In this video, we'll determine the output voltage if the input voltage is 6e to the negative 6 u of t volts. It also says to use the system function. So we have to determine the system function of this network, which consists of a capacitor and two resistors. So the system function is the response to an input function. So what we need to do is apply an input function as an input function V in, one impulse delta t, and then determine what that output is, and that will give us the system function h of t. So it might be easiest to do this in frequency domain. So if we convert to frequency domain, our input's function, the Laplace transform of that is just 1. Our 500 millifarad capacitor becomes 2 over s ohms, and our resistors are unaffected. And our output function as a function of s will be our system function as a function of s. And then we can analyze in the h domain. Once we find h of s, we can just multiply that by the Laplace transform of our v in of t here. So in doing so, then what we need to find is our transfer function, our system function. So that's easy enough to do. We can just do a voltage division. There will be no current flowing through this 1 ohm resistor, so we can just do a voltage division. The voltage across the 2 ohm resistor is the output voltage, so that's our system function in the S domain. So once we do our voltage division, V in times our 2 ohms divided by our 2 ohms plus 2 plus S ohms. If we multiply this then by S over S, we get 2S over 2S plus 2, and then we can divide out the 2. So we end up with just S over S plus 1, and that's our system function in the S domain. However, if we want to convert that to the time domain, we don't have a rational function. So we've got to convert that so that we're going to end up with the impulse function also as a response. So we can change that. That's equal to 1 minus 1 over s plus 1, and that's easy enough to do. Just divide s plus 1 into s, and we get our system function as the sum of two rational polynomials or rational functions of s, and then we can convert that to time domain. So our time domain function then is this, R1 converts back to an impulse function, delta t, and we have minus our e to the negative t u of t. So there's our system function in the time domain. We can then use that to help determine, if we want to find our v. We don't really need that in the time domain because we're going to determine the output in the frequency domain. So our input function as given, 6e to the negative t u of t, that in time domain is our 6 over s plus 1. So we just need to multiply that by our s over s plus 1. When we multiply that out, we have 6 over s plus 1 times s over s plus 1. That's a rational function, 6s over s plus 1 squared. So then we can use our partial fraction expansion. That's going to be our a over s plus 1 squared plus b over s plus 1. We can use our cover-up method to find a. Cover-up method to find a. We just get a is equal to negative 6, and then we can do the first derivative. And again, insert s is equal to 0. We get negative 6 over s plus 1 squared plus 6 over s plus 1. And then we can convert that back to time domain. So our output voltage then is 6e to the negative t. And then this multiplies by negative t because it's a negative 1. So that's the 6, and there's our 1, and it's all a unit step function. So that's how we can use our system function. Made it very easy by analyzing this in the frequency domain. In summary, what we found was that our input function in time domain, our system function in time domain, and then our output function in time domain. But we found it by converting to the S domain first and applying an impulse function of 1 and analyzing that in S domain to find h of s, and then just multiplying. But we did have to take the Laplace transform of our 6e to the negative t u of t and multiply that by h of s. So now that we have that, what if we change our input function? What if we change our input function, same network, to t u of t, and we use that same system function? What we found was that system function h of s is what we want. H of s was equal to, what did we find that to be? S over s plus 1, right? S over S plus 1. So if we want to find our V out of S, or we'll call it VO, our VO of S, that's just equal to our V in of S times our H of S. So we don't need to determine anything about this capacitor anymore, even though we've already done that, because we're just going to represent this function as H of S is equal to S over S plus 1. So now we need to, and here's our VO of S. So now we need to determine our V in of S. Our V in of S, the Laplace transform, or Laplace transform of V in of T, that's just is equal to our 1 over S squared, right? It's our TU of T, so that's 1 over S squared. So what we have here is 1 over S squared volts, plus or minus, and we have our VO of S is equal to 1 over S squared, whoops, not plus, but times our S over S plus 1. And that's just equal to, we can cancel out one of the S's, so that's just equal to 1 over S times S plus 1, or equal to A over S plus B over S plus 1. We can find them both with the cover-up method. A, if we cover up the 0, just cover up the S and plug in 0. A is just equal to 1, so it's equal to 1 over S. If we cover up the S plus 1 and plug into negative 1, B is equal to negative 1, so we get negative 1 over S plus 1, and our inverse Laplace transform of that gives us a U of T minus e to the negative T U of T. So we can just do it like that, and unit of volts. And if we wanted to apply a different function, if we want to apply a sinusoidal function at the input here, then we can just use our sinusoidal Laplace transform, and that what we'd be changing, right, what we'd just be changing is the V in of S. All right, that's it for this video.